Hello, everyone, and welcome to another live stream of Chemistry 223 through Portland State University's Learning Center. I'm Travis, and I'm here to talk to you today about the solubility product constants. And if we have some time, we're going to go into Lewis base acids and entropy, and the change in entropy and spontaneity, and other fun things like that. First, I want to post a few links. So first link in our chat here is going to be to the Learning Center. That's the Learning Center's website. It's on pdx.edu/learning center/tutoring. There's also a link to the Facebook page. You can follow them on Facebook, which I definitely recommend. You can also follow the Learning Center on Instagram as well. Just learning about our new services as they come out. And definitely, if you ever have any questions outside of this stream, tune in and schedule an appointment through Penji for one of our tutors. We have tutoring for all the sciences: biology, physics, chemistry, math, and a bunch of other great resources as well. All right, so let's get started here. Switch here. Here's my iPad. So we're going to start out by talking about the solubility product. So the solubility product. This is the solubility of a substance. So if we were to add two mixtures together, or if we add, if we add a solid into water, basically, eventually the water would, if that solid is dissolvable in water or soluble in water, it would start to dissolve into the water. But at some point, it's going to get super saturated. So let's start out by saying the solubility of a substance can vary from essentially zero, and this is for things that are completely insoluble or just barely soluble, to infinity. And something that has an infinite amount of solubility is basically, we call it miscible, which means you can mix any two bits of it and they're going to continue to be completely soluble in there. And for things that have a finite soluble, we call, they're going to reach this level of saturation. So saturation is when a solute with finite solubility can yield a saturated solution when added to a solvent. In an amount exceeding its solubility. So we can see this in our everyday life if we add stuff like sugar or salt to water. If you took salt and added it to water, it would start to it would start to dissolve eventually, right? Especially if it's hot water. We're going to get to this level of saturation eventually, where you can add a bunch of salt to the water. It'll continue to dissolve, but eventually you're going to end up with salt kind of just chilling on the bottom of the glass or the bottom of the pot that you've heated it up in. This is when the salt water has been fully saturated, which means it's reached this equilibrium state where it's dissolving at the same rate that it's reforming. There I am. So it's dissolving at the same rate that it's reforming. And at that state, it's basically at this equilibrium state. So the rate of its rate that it's dissolving at is equal to the rate that it's reforming at, and the level of precipitation doesn't really change. If you were to continue to add more solid to that, more salt in this case, we would just see more and more salt build up at the bottom. It's not going to dissolve at a higher rate anymore. It's reached this maximum rate. So at the equilibrium, so any excess of solid dissolves at the same rate. Should be a the in there. The same rate in which the aqueous ions combine to precipitate. Which will, and that precipitation basically reforms the solid. And we can write kind of a general balanced chemical equation for this. If I have two compounds, I'm going to call one M and one X. And let's say the ratio for them is MPXQ, and that's a solid. And this is where M and X can be any two compounds, M being kind of a positively charged compound, X being a negatively charged compound, and P and Q are just kind of the ratio of which we have to add these together. So like I said, this is just a general formula. This is going to disassociate into P moles of M. I'm put a lowercase m up there just to be the charge, plus, say, Q moles of X and minus. I know this is a little abstract, but this lets us write a generalized form of the constant of solubility, which is going to be equal to the concentration of M plus to the power of P times the concentration of X in minus to the power of Q. So if I were to just throw an example out, we could say if this was, say, sodium chloride as a solid, it would be in equilibrium with sodium ions in their aqueous state plus chloride ions in the aqueous state, and the KSP of that is going to equal concentration of sodium times the concentration of chloride. And these are both going to be to the first power because the stoichiometric ratio, the coefficients there, are going to be 1 and 1 for sodium and chloride. So these are ones. If that stoichiometric coefficient was different, if it was a 2, we would have to square the concentration of that compound in the solubility constant equation. And notice that we don't count the solids or gases in our equilibrium constants, just like when we were doing acid and base, and for Kas or Kbs. The same is true for, we don't count solids and liquids. We do count gases and aqueous ions. Only gases and solutes are represented in that equilibrium constant. So we're not counting the solid form of it. So we don't count the salt. We don't count anything else that would be solid or the precipitate in there. So we can use this, if we can find the solubility constant, to find the concentration of the two compounds at solubility. And let's try using this idea and some of the stuff we learned from the acid-base chemistry. There it is, on this problem here. So this is telling us that the KSP of lead diiodide is 1.4 times 10 to the negative 8. So we want to calculate the molar solubility of lead 2 iodide. So I'm going to write first the balanced chemical equation for this dissociation. So we have lead, big capital P, lowercase b, and then 2 iodides, which is a solid, and that's going to be in equilibrium with, or form, Pb aqueous, which is going to be a 2+ ion, because we know that iodine is a -1. And there's 2 of those. So getting those charges right is useful because that helps you tell that molar stoichiometric coefficient there is going to be a 2. So we know also that our KSP is going to be equal then to the concentration of lead, 2+, times the concentration of iodine minus squared. And we can determine that, what that is going to be, using the ICE table, just like we did with our acid-base chemistry. So using an ICE table, we know the initial concentration of all of these. For the solid, it never matters. But for the initial state of the 2 ions before they dissociate is going to be 0. The change in the lead concentration we can say is plus X. And then the change of the iodide is going to be plus 2X, because there's twice as much iodide as there is lead. So at the end, the concentration at equilibrium of the lead is going to be X, and the concentration of the iodide is going to be 2X, twice that value. And I can write that down here. Pb plus, or 2+ is going to equal X, and concentration of iodide is going to equal 2X. So plugging those values in to our KSP equation, we can see that KSP is going to equal X times 2X squared. And it's important to put those parentheses around that 2X in that equation, because we need to square not just the X, but also the 2. So I can rewrite that KSP is equal to X times 4X squared. So 2 times 2 is 4. And then doing this multiplication, I can see that KSP is going to equal 4 times X to the 3rd power. And then we just need to plug in the value they gave us for KSP. 1.4 times 10 to the -8 power is going to equal that 4X cubed. And now we just have to solve for X. To solve for X, we can divide each side by 4. And then take the cubed root of that. Let me make a little bit more space. So the cubed root's like that. It has a little 3 up in the index there. Same over here. Take the cubed root of that whole fraction. And we can then solve for what X is going to be. So if I did that on my calculator here, this is like a TI 83, 84 style calculator. To do the cubed root, I have to go into the math function, and I have it number 4 here listed there. When I do that, it puts a little 3 up on the top of the square root, which is the index for it. So it's taking the cubed root of whatever I put under there. I'm going to use a parenthesis, 1.4, use this little EE for times 10 to the power of -8. Close my parenthesis, and then still under that square root bracket, put divided by 4. So making sure I have all that in parentheses is always a good thing. Anytime you're isolating your numerator and your denominator, always try to put the whole thing in parentheses. It doesn't always hurt to add more parentheses if you need them. And we hit enter, and that's going to be 0.0015. If I were to write that in scientific notation, that would be 1.5 times 10 to the -3, which is our molarity of X. Well, what does X equal? X is equal to, we had it over here, the concentration of lead 2 plus. So that means the concentration of Pb 2 plus is going to be equal to 1.5 times 10 to the negative 3 molar. So is that the same for the concentration of iodide? Iodide was 2x. So I have to multiply this value here by 2. So doing that, I can see that the concentration of iodide is going to equal twice that value. So going back to my calculator, if I just multiply this value times 2, I get 3 times 10 to the negative 3. Molar, which is the concentration of your iodide. So that is the concentration ratio that you had. So if you had that much lead and that much iodine in one thing, you'd reach that saturation point. If you added a little bit more of one or the other, it would actually precipitate out. That's like the tipping point between everything. And we're going to talk about that next, is kind of how can we predict how that precipitation is going to flow. Is it going to flow so we're going to add precipitation, or is it going to stay dissolving for a while? And we can do that based on this idea of the reaction quotient and how it compares to the solubility constant. So we can calculate the reaction quotient which is QSP of any solution using basically the same formula we had for the KSP value. In this case, we just call it QSP, which is equal, I'm going to just put it in the same form as we had before, capital M to the power of lowercase m plus, so that's whatever the positively charged ion is, to the power of whatever its coefficient, the stoichiometric coefficient that it has, times the concentration of the anion to the power of whatever its stoichiometric ratio is. So for sodium chloride, this is going to be the same thing. That'll just be equal to the concentration of Na plus times Cl minus. And again, they're both to the power of 1 because their stoichiometric coefficient is 1. We usually just ignore it because if you take anything to the power of 1, it doesn't change the value. And if we compare, so we say by comparing the QSP versus the KSP value, and you need to know the KSP value. Usually, there's a lot of tables for this. I'll show you in my browser here. So this is the solubility products. It's an appendix J of the OpenStax Chemistry 2E textbook, and they have listed on there the KSP at room temperature, 25 degrees C, of all these different compounds. It's probably all the ones they're going to use in that textbook. This is the one they just put in there. And they kind of group it based off of the positively charged compound that's in there. So silver ones, if you have potassium something, you can look there, and so on. So it's a real nice way to find what you're looking for. You can also do a quick Google search, say, what's the solubility constant of this? And then if you use it in your homework or on a paper or something like that, just cite where you got it from. and then your teacher can know then where you're getting your information from. Continuing, so by comparing that value to the KSP, we can predict how the reaction progresses. Or progress. How will it progress? Let's use proper English. So there's three different states. The QSP can be less than the KSP. The QSP can be greater than the KSP. And the QSP can be equal to the KSP. So we can try and determine what each of these is going to mean. If the QSP is less than the KSP, that means that the ratio of the two concentrations in there hasn't quite reached saturation yet. So I'll put on here, not reached saturation. Therefore, nothing precipitates. Everything is fully dissolved. So you could probably guess that if the QSP is greater than the KSP, that means the solution, we call it supersaturated. That means it's not only reached saturation, it's gone beyond saturation. So that means we're going to have some precipitation, if I can say words. Because up until the point of saturation, everything's going to be fully dissolved. And at that point, or anything you add after that point, excess of saturation, you're going to have that solid form. And this could be in various different ways. If you were to increase the concentration of one of them and leave the other one the same, you're beyond precipitation, and some of it's going to bond together. If you reduce one of them down, then you're going to have a little bit as well. But we can, if their two are equal to each other, if the QSP is equal to the KSP, then the solution is at saturation. And this saturation is basically the same as the equilibrium point. So we say at that equilibrium, which I call the tipping point. It's really hard to get it exactly at the tipping point. To a certain number of sig figs, that's fine. Remember that these KSP and QSP values it's all based off of the temperature. So if the temperature was to fluctuate just a little bit, if a cool breeze came in, you might see a little bit more precipitation. If a warm breeze came in, it might stay dissolved a little bit longer. So it's really just kind of like a sweet balancing point and tipping point between them. If you stir it up a little bit, you actually add a little bit of energy into that, so you'd actually get more things dissolved, less precipitation. And to get those values exactly right is really hard. But you should see that basic idea of at that equilibrium. Anything past that, you're definitely going to see some solid forming in there. So let's try this concept out using the general idea comparing these values for a problem. I guess we're not really going to compare them, but we're going to use that idea here. So here we have clothes that are washed in water, and it has manganese. It has, I guess, manganese ions in there, which are 2+. And if the concentration is exceeding 0.1 milligrams per liter, which is 1.8 times 10 to the negative 6 molarity, they may be stained by the manganese upon oxidation. But the amount of manganese in the water can be decreased by adding a base to precipitate it, because manganese in the presence of hydroxide will actually precipitate, create a solid, thus making it so it doesn't stain your clothes. So they're asking what pH is required to keep the manganese equal to 1.8 times 10 to the negative 6 molar. So the question is, do we want this to be acidic or a basic solution? If it's acidic, well, we would have those acidic ions would kind of bond to any of the OH ions we have in there, any of the hydroxide ions. So it wouldn't be able to have enough OH to actually bond onto the manganese. So it's going to have to be some sort of basic solution. So we would expect the pH to be greater than 7. I'm just going to keep that in mind. That's my double check to see if I did anything just about right. So I can write out my balanced chemical equation for this, writing just that equilibrium state for the solid. So manganese OH minus, or manganese dihydroxide solid is in equilibrium with Mn2 plus aqueous plus 2 OH minus. Notice again it's 2 because this is a 2 here. There's 2 hydroxides within this solid, so we got to make sure that once it's disassociated, we have twice the concentration of them. Aqueous. And writing the KSP value out, KSP is going to be equal to 2 times 10 to negative 13. We can find that in our book, I bet. Switching back to my browser. Twink. Manganese OH. Well, that's way different than what I had in there. Oh, that's magnesium. That's why. Manganese is down here. That's better. 2 times 10 to the negative 13. And that's what I wrote down there. So knowing that our KSP is equal to the concentration of manganese 2 plus times the concentration of our hydroxide squared, we should be able to solve this problem because we know what the concentration of the manganese needs to be in there. So I can say KSP is equal, and I know what the KSP is as well, so let's just write that in right now. That's 2 times 10 to the negative 13 is going to be equal to 1.8 times 10 to the negative 6 times the concentration of hydroxide squared. Now we can solve for this using algebra. So I'm going to divide off my 1.8 times 10 to the negative 6. Which is then going to leave me the concentration of hydroxide squared. And then I need to take the square root of both sides. To get my concentration of hydroxide. And let's do that. Taking square root of, put a parenthesis, 2 e to the negative 13, close the parenthesis, divide by, open the parenthesis, 1.8 e to the negative 6 gives me 3.33 times 10 to the negative 4. Let's say it's 3.3 times 10 to the negative 4. My sig figs. And that's going to equal the concentration of hydroxide. But that's not what they were asking. They were asking at what pH is required to keep this. So we want enough base in there, basically, to keep there. So how do we calculate the pH? Well, we have the hydroxide concentration. So we can calculate from that the POH, which is going to equal negative log 3.3 times 10 to the negative 4 molar, which is equal to 3.48. You do the math, negative log 3.3 e to the negative 4. There it is, 3.48. But that's not our pH. To get their pH, we have to equal 14 minus the POH, which is equal to 14 minus 3.48, which gets us to 10.52. There you go. So if you keep a really basic thing in there, a solution in there, no manganese stains on your clothes. And there's the pH that you want to make sure you keep it at. So we're going to go on, if there's no questions, and talk about Lewis acids and bases. And a Lewis acid and base is similar to what we've dealt with in the past, just in this time it's not necessarily a hydrogen donor or a hydrogen acceptor. Now we're talking about kind of different species which can kind of operate as an acid or a base in a different way. So we talk about this idea of a coordinate covalent bond. Which occurs when one of the atoms that in the bond provides both bonding electrons. So our normal acid base with the protons, since proton, the hydrogen ion, has no electrons of itself, both of the electrons are provided by the base usually. So those are kind of a subset of the Lewis acid and base. But not all Lewis acid and bases have that hydrogen ion in there. So one of the atoms in the bond provides both bonding electrons. So in that situation, we call the species which donating the electron pair is called the Lewis base. So this is the same as what we've dealt with before with the bases. Since the hydrogen ions never have any electrons for themselves, the other complex or the other species is usually the one who provides all the electron pairs. So that's going to be the base of the situation. And similarly then, the species accepting the electron pair is called a Lewis acid. So the Lewis acids are most likely going to be positively charged, while the Lewis bases are going to be negatively charged or neutral. So things like ammonia and other things like that can operate as Lewis bases as well as the bases that we normally do, because they have a full set of electrons that they can donate to this bond structure. And the product of these the product is called a Lewis acid base adduct. An example of this is with the fluoride ion, this is a fluoride ion that's negatively charged. It's got four pairs of lone pairs around it. And when it bonds to the boron trifluoride, so boron bonded to 3 fluorides already, putting in the electron, the lone pairs on those. Boron's neutral now. It's really happy with 3 bonds, but it's able to, because it doesn't have a full quartet, it's able to accept another bond from fluoride here. So this is going to produce this adduct, where now we have boron tetrafluoride. And really that boron's going to be negatively charged, but we can just draw the whole complex species with a negative charge on the outside. And this is an example of a Lewis acid and a Lewis base. So in this case, this is my Lewis acid, my Lewis base, because it's providing all the electrons for that bond. Boron, all of its valence electrons are used up, but it still only has 6 in its shell. Be 2 in this bond, 2 in this bond, 2 in this bond. It hasn't got its full octet yet. So it really wants, it's capable of making another bond with that. But that leaves it, so now it's slightly unstable. It's at a negative charge. So the boron trifluoride is a Lewis acid, and the boron tetrafluoride would be the Lewis acid base adduct, or just the adduct. This same sort of process happens as well when you form complex ions comprising of a central atom, usually a metal ion of sorts, surrounded by multiple different ions or molecules. We call them ligands or ligands. Surrounded when this happens, there's a certain equilibrium constant for this type of reaction as well. Excuse me. That equilibrium constant for the reaction of a metal with an ion or other ligands is called the formation constant. There's also an idea when these ligands disassociate from each other again, that covalent bond, or we called it the coordinate covalent bond, breaks from these complexes. There's a dissociation constant for that as well. So I can say Kf is what we call the formation constant. And Kd for dissociation is the dissociation. And they have a relationship where the Kf is going to be equal to the inverse of Kd. And this makes sense because if you were to write out the equilibrium constant there, it would be the products divided by the reactants. Well, in the case of the formation of the complex, the two ions would form into a solid object. Or no, maybe not, so it's an ion still. So it would form into this complex. So we'd have this complex divided by the two ions disassociated. Or in the dissociation complex, you take that same balanced chemical equation, we flip it around, and now we have the dissociation as the product and the complex ion formation, or complex ions on the bottom of that reaction. So that gives us this relationship between the K of formation and the K of dissociation. So let's try a problem with this. We're going to say, where's my green? Calculate the concentration of the silver ion in a solution with a concentration of 0.10 molar with respect to silver ammonia plus. Whoa, what happened there? So this is telling us the concentration of the solution, what that formation is going to be, and we need to calculate the concentration of the silver ion ultimately. So we can take this reaction. If I say it would be silver ions, Ag plus aqueous. Oops, I don't need that concentration in there. Plus the ammonium in H3. Nope, that's neutral. And we're going to have to put a 2 in there to keep it balanced, because this is really 2 plus. Yeah. No, wait, that's not 2 plus. Silver is Ag there. Yeah, so silver's 2, just 1. And that would make sense. It's the whole thing is plus 1. So that's an equilibrium with the formation of Ag and H3 2 plus. Notice the charge is balanced on both sides of the equation. I have a +1 charge over here, and I have a +1 charge over there. This is still going to be aqueous. So we can write the K of formation based on this now. The K of formation, and it's formation because we're creating this complex on the right side. The product is this complex formation, which is going to be equal to the products, Ag NH3 2 plus divided by concentration of the reactants squared. You got to square it because we had a stoichiometric coefficient there of 2. Now to find this, we would first need to find what is the K of formation of this compound here. So I'm going to switch back to my browser. Let's see if we can find this. We're looking for silver. Here's silver. Going down silver. Oh, tell me it's here. Is it not there? Of course it's not there. Let's do a quick Google search then. Let's just type in Ag NH3 2 KF. So that's what it's telling us here. 1.7 times 10 to the 7 is my KSP, or K of formation for that. So this needs to equal 1.7 times 10 to the 7. Now if I do my ICE table for this, my initial concentration is what we need to find out for the complex ion. Or we know that, I'm sorry. We start out with the initial concentration of 0 and 0 for the ions. Let me copy this down here so I know what it's associated with. There we go. That's a little easier to follow. This we said was 0.01, just 0.10 is the initial concentration of that complex ions. And we look at the change in these. The change, this is going to be going down by some value. The complex is going to reduce by some value, while the silver is going to go up by that same value, and the ammonia is going to go up by twice that value. So our final equilibrium, or at equilibrium, the final concentrations are going to be x, 2x, and say 0.10 minus x. So I can then plug that into my equation, 1.7 times 10 to the 7, which is going to be equal to 0.10 minus x, our products, divided by x times 2x squared, which we can rewrite for x to the third. Now we just need to solve for x. we can assume, since this is very big and in relationship this is going to be very small, that X value of concentration, we can assume then that X is much less than 0.10, this value here, which simplifies our equation. We can then just drop this out. Solving then for X, we can then say that 4x to the third times 1.7 times 10 to the 7 is going to equal 0.10. Multiplying this over, we end up with x to the third is equal to, or really I'm dividing it over 4 times 1.7 times 10 to the 7. Just distributing this 4 to this guy and dividing both of those over, so we get our x alone. We can then take the cubed root of that, so x is going to equal the cubed root 0.10 divided by 4 times 1.7 times 10 to the 7. Put this in our calculator and hit math. Number 4 is the cubed root. 1.10 divided by 4 times 1.7 times 10 to the 7 is going to equal 0.0113. So I can just round that, to 1.1 times 10 to the negative 3 molar. And that is going to be then the concentration of the silver, because silver is equal to the X. So I can say concentration of Ag plus is going to equal 1.1 times 10 to the negative 3 molar. If we wanted to find the concentration of ammonia, we can just double that. So concentration of NH3 would equal 2.2 times 10 to the negative 3 molar. Verify that. Oops. Oh, I don't have that there anymore. This value times 2, 2.2. This is one of those cases where it's actually more like 2.3 because of the sig figs. So I'll fix that. And there we are. So at those are the concentrations that they would be at. They only really asked for the silver, but might as well go the full way at that point. And that's it. So we're about out of time for this. We didn't have enough time to get into entropy and spontaneity, but we'll cover that next week as we go into the relationships between entropy, enthalpy, and Gibbs free energy and stuff like that. Have a great week and enjoy. Thank you.